let's review population growth. The population in humans, animals, bacteria, they follow usually, the population growth follows the exponential function. In general, at the beginning of the population, at the beginning of time, we start with a specific amount of organisms, and in the future we increase this exponentially. When we get sick, for example, and we get sick with an infection, then the number of bacteria in our body increases exponentially. The formula for the exponential function is f of x equals to a number, k, times a base, let's say b, to the x or to a function of x, let's say x over a number m. Let's give a specific example. Suppose that you have a bacteria that the neighborhood of bacteria starts with a number of 300. So there is a 300 count of bacteria in a specific organism. And we know that this number increases exponential with a factor of 2 to a specific time. Let's count the time in days. So every day it increases exponentially to a factor of 2 over, let's say, a number of 30. What does it say? This says that the first day, at the beginning of time, when t is equal to 0, then your function, the number of bacteria, and this will be the number of counts, the count of bacteria in the specific organism, is going to be the f of 0. And the f of 0 in this case will be 300 times 2 to the 0 over 30. Now, the exponent of 2 is 0. So 2 to the 0 will be 1. So this means that the initial number of bacteria in the organism is going to be 300 of them, since this number right here is equal to 1 at the beginning of time when t is 0. Now, after 1 day, we will have a number of bacteria that is again modeled by this function, and this will be 300 times 2 to 1 over 30. This is the 30th root of 2, very close to 1. So we can see that at the beginning of time, after 1 day, the number of bacteria will not increase much. It will be a number close to 300. What will happen though after, let's say, 2 days? After, let's say, 30 days? When this means that we need to look at the f of 30. F of 30 will give us the number of bacteria after 30 days. And this will be 300 times 2 to the 30 now, because this is the time divided by 30. And this is equal to 300 times 2 to the first. So this means that this will give us 300 times 2, that is 600. So basically, after 30 days, the number of bacteria in the specific organism would have doubled. After 30 days, the number of bacteria became from 300 that they were at the beginning, 600. So what happened is that they doubled. Now, let's see this on a graph so we can visualize what's happening. We can see right here the graph of the population of bacteria based on time. The x right here is the time, and the formula, the function that we use is the same, 300. At time 0, meaning at the beginning of time, we have the specific point that is the y-intercept, that is the f of 0. The f, the function, the p, in this case, as I denoted right here, that is going to give me the number of counts of bacteria at the beginning of time. And this is equal to 300. Since the x is 0, 2 to the 0 will be 1. As we calculated before, we can see right here in our graph that after 30 days, almost 30 right here, after 30 days, the bacteria will double and they will become 600. If we want to go further, then we can see that after, let's say, 60 days, let me bring this down, after 60 days, right here, the bacteria will become 1,200 of them. 1,200. This will be true after 60 days. 60 is the number x. Let's look at the algebraic solution of that. The f of 60 is going to be, again, 300, because I'm using the same formula, times 2 to the 60 now, divided by 30. But this is equal to 300 times 2 to the second. And this is 300 times 4. That is equal 1,200 counts of bacteria. So what we can see, either algebraically or in our function, is that we can use exponential functions right here in order to calculate and to review the population growth of organisms. Assume now that we use the same formula as before, but what we need to calculate is when the number of bacteria will reach, let's say, 10,000, because we are working with nursing and we know that when the specific bacteria reach a population of 10,000, then it becomes dangerous for the organism. Our function will remain the same. The function that we work with is p of t equals to 300 times 2 to the t over 30. What we want to know now is when, and remember t is what counts the time in this case, so we want to know when the total count of bacteria, so when the total count of bacteria, meaning the p of t, will be equal to 10,000. Why? Because we know that for the specific bacteria, when they reach the population of 1,000, then it's dangerous for the organism. So what we want to calculate is basically the t when the pt is equal to 10,000. So the function that we want to, the equation that we want to solve is the following. And this is an exponential equation. In order to solve an exponential equation, we need to use logarithms. The first thing is to isolate the power by itself. So we will divide both sides by the coefficient of the power, that is 300, in order to get rid of the 300 on the right side of the equation where we have our power. So we have 100 divided by 3 equals to 2 to the t over 30. Now, we need to use exponents in order to solve this equation. We need to use logarithms in order to solve this equation. Since our base of our power is 2, we are going to use the logarithm with base 2. So we need to calculate the log with base 2 of 100 divided by 3 equals to the log with base 2 of 2 to the t over 30. At this point, we can use the rules of logarithms in order to simplify our equation. So, on the right side, I have the log, and I'll keep it for the moment as it is, of 100 over 3. And on the left side, I can bring down the exponent using the rule of logarithm that tells me that if I have log x to the k, this is equal to k times log of x. So this is going to be equal to t over 30 times log with base 2 of 2. Now, remember the log of a number on the same base is equal to 1. So I have managed to change my equation to the following simpler equation that tells me that t over 30 is equal to log of 100 over 3. And I can solve now the t equal to 30. So I multiply both sides by 30. And I simplify the 30 from the t, and now t is equal to 30 times the log of 100 divided by 3. Now I will use the quotient rule for logarithms in order to split that to log with base 2 of 10 of 100 minus log with base 2 of 3. Or I can leave my answer as it was if I am not allowed to use calculators. So t is equal to 30 times log of 100 divided by 3. If you want to approximate your number, 100 divided by 3 is 33.3. That is very close to 32. The log of 32 with base 2 is 5. So if you want to approximate your number, then t is going to be equal to 30, is going to be approximately equal to 30 times 5 point something, and the final answer will be something like 150 or 151. What does this tell me? This tells me that after 151 days, the population of bacteria in the specific organism is going to be 10,000, and this is going to be dangerous for the specific organism.